The following audio recording has been designed for learning purposes only. Do not share, distribute, or provide any type of copies, or this audio lesson will not be made available to you. Good luck with today's lesson.
Okay, chapter 18. So the big math parts, the chapters with a lot of calculations, that's done. We'll see a few in this chapter. 19 is what's 20. We'll have a few smaller ones, and then 22 and 23 are almost all qualitative. So we're through the big math calculations. I saw over the break that some people were doing the homework. That's good. I mean, they're really going into it. Other people are kind of lagging behind. Don't want to do that. Email me if you have any questions. So, thermodynamics.
Yeah.
Thermo for heat. Dynamics for work. And it was started out with a question in mind. And they just wanted to know, if you were going from, say, Podunk to Gooberville back in the 1800s, how much coal do I need to bring to get to from Podunk to Gooberville? If I don't bring enough, I'm going to be stopped out in the middle of nowhere. If I bring too much, then all I've done is used up coal to haul coal. It's a waste of coal. So to go from Podunk to Gooberville, and that was the only question they had in mind. In the process, they created the laws of thermodynamics that govern everything. Thermodynamics governs everything down from subatomic particles all the way up to the circling of groups of galaxies. They govern black holes. They govern oceans. Everything is governed by thermodynamics. If it's thermodynamics is not properly modeled in your theory, you're wrong. It's accepted as absolutely wrong. So what they're asking here is, what is the efficiency of the engine? So to study this, to figure out how efficient an engine is, because engine is going to do work, but it also produces a lot of heat. So they wanted to know what they can do with this engine. What amount of work can you get out of it? Okay, so that's what it came down to. But then in the process, they created an entire structure that underpins every science. Not only the sciences, but anything that if you're just interested in, calories, nutrition. The base thermodynamics. The idea is that everything has a certain amount of energy that you use. If you don't use the energy, it gets stored. You count on that. You don't count on something every time you eat an apple that maybe it's 75 calories. Oh, maybe it's 2 million calories. It doesn't shift. Thermodynamics guarantees this. So how many laws of thermodynamics are there? 4, correct. They're always the last one that's forgotten because it was the last one, but it's the 0th law. And they don't have it in the book. In physical chemistry, which I taught for many years, it was always the first thing you did. But why would they? So they came up with the first, second, and third law, and then later on, about 40 years later, they came up with the 0th law. Now, it's got to be pretty damn important to instead of making it the 4th law of thermodynamics, to say, nope, shuffle everything over. They would have made it the first law if they would have thought about it. Instead, they made it the 0th law. It's so important that they actually had to shift it back. So we're going to talk. This is the only thing so far this semester that hasn't been in the book. So this is important. It's not too bad. So 0th law of thermodynamics. We'll go through each of the laws. So it was in the 1920s, and I do this every semester. I always think it starts with a W. I can't remember the name of the physicist, but he pointed out, he said, wait a minute, hold on. How can we have any laws of thermodynamics if we haven't stated this? And everyone agreed. Now it's like this. This is from mathematics. Reflexive. This is the reflexive property. A is equal to A. You might say, well, duh. But if that's not true, then mathematics doesn't work. For instance, so if you have that, well, what are you doing to solve for x? Get rid of A. Well, how can you do that? Well, you're guaranteed that A is equal to A. So if you add that to both sides, then you have here. If A was not equal to A, it was slightly off, then you wouldn't be able to subtract this. You'll have some part here, and you couldn't solve the problem. So as simple as it may seem, you have to state that A is equal to A. No way around it. If you don't, then you can have something like in the Hitchhiker's Guide to the Galaxy. Actually, it's the restaurant at the end of the universe. I think is the... is a Hitchhiker's Guide to the Galaxy. They have the improbability drive, and it's based on bistro mathematics, the mathematics of restaurants. And, of course, it's a funny book, but it's the idea is that if somebody makes a reservation for 6 people, all you can be sure of is that it won't be 6 people who show up. It might be 5, it might be 7, it will not be 6. So in the math that governs what's called an improbability drive in a spaceship is a number is anything other than itself. That's the basic rule. So if you do that, then you get all kinds of funny, weirdo stuff. But here we assume that a number equals itself. Okay, so that's basically what we're doing here. It said at thermal equilibrium. So we have 3 systems. They can be anything. They can be solid, liquid, or gas. Here we'll just make them appear like solid blocks. A is in thermal equilibrium with B. B is in thermal equilibrium with C. So at thermal equilibrium, if the temperature of A is equal to the temperature of B, and the temperature of B is equal to the temperature of C, then what do you suppose? Temperature of A is equal to that of B. B is equal to C. What do you suppose you can draw from that?
A equals C.
No. Even though they're not touching, the temperature of A is equal to the temperature of C, but only at thermal equilibrium. So you take these 3 boxes, one can be gold, one silver, one lead. You just jam them together, get them in thermal equilibrium. If you take the temperature of A, then you know the temperature of C. All right, so why would that be important? Well, if you're testing anything with a thermometer, make this a little longer, a little wider. So this is the a thermometer here, up close. And then you have this system, whatever you're studying here. Let's say this is a solution outside of it. So this is a beaker. And you have your mercury in here. And this is made out of glass. So you put the thermometer into the solution. Well, you know that the solution, so once the thermometer stops moving, the mercury stops moving, the alcohol stops moving, the temperature of the solution is equal to the temperature of the glass. You're not touching the solution to the mercury. If you did, it might react. At worst, it would just plop down, or at best, it would plop down to the bottom. So the mercury has to be behind this glass. So the temperature of the solution is equal to the temperature of the glass. The temperature of the glass must be equal to the temperature of mercury. So the temperature of the solution must be equal to the temperature of the mercury, which is what you're looking at in the thermometer. You see what the mercury says. So what it's saying here, this is what you can write. You can also state the zeroth law as thermometers work. And everything that we do, remember from chapter 6 for the thermochemistry, we did calorimetry experiments. You did it in the lab where you measure the temperature changes as you add acids and bases together. If we can't count on thermometers to work, then we can't count on any temperature that we see. So if we go back to, we're actually going to use this for one of our labs. This is the heat, specific heat, mass, temperature change. So to find the heat, and the heat is, the enthalpy is related to the heat divided by the number of moles. So the delta H, which is the thermodynamic property, is governed by the heat. The heat is found through the temperature, and the temperature is found from a thermometer or any other temperature gauge. But if the thermometer didn't work, we couldn't trust this, we couldn't trust this, we can't trust this, and then we can't trust this equation, which is going to be the big one for us this chapter. We couldn't trust this term, can't trust this one, so we can't trust the free energy. So all of thermodynamics collapses. So even though it's quite obvious to everybody, it's one of these things that just so this has to be stated. So on my exam, you should know this. At thermal equilibrium, if you have three different systems and they're in a line, or in some way that A and C can't touch, they can't exchange heat, then this is true. And a shortcut way of saying it would be thermometers work. And the thing about, for my exam, if I asked you what's the 0th law and you want to put thermometers work, fine by me, because that's exactly what it means. But this is the more precise. And you could say, if you want to be really in general, you could say thermal gauges work. Thermometers and thermal gauges. So anything that measures temperature is based off this. So when people say, well, measure the temperature directly, you can say, if you want to be, smart aleck, your later classes, and say, well, we'll use the thermometer to measure the temperature directly, and say, we're never measuring the temperature directly. We're measuring it through here. We're using the 0th law. The only way you could do this is if the mercury and the solution were touching. But then how would you use the mercury to tell the temperature? It wouldn't do anything. It would just lay on the bottom. So you need to have it surrounded. So you're never, all of our thermal, anytime you do anything with a thermometer, it's an indirect measurement. But the 0th law says, don't worry about that. It is direct. It is a direct measure. Okay, so that's the 0th law. All right, so you should know that. And let's do the first law here. So that's the only thing that so far, I think there's one more thing that we cover later on that isn't directly in your book, but that is. So there are 4 laws: the 0th, the 1st, 2nd, and the 3rd. So what's the first law? Okay. So in words, you can say that this is the law of conservation of energy. And you could say that energy is neither created nor destroyed, only changed in form or transferred. So energy is, there's a set amount of energy in the universe. It's always been there, always will be there. It's just different forms of it. Potential energy can be changed to kinetic energy. There's potential energy. Now for this, there's potential energy for the marker. I just changed it to kinetic energy. I'll just push it over. And the potential energy it had, because it was in the gravitational field, but as soon as it started moving, it became kinetic energy. So lots of ways of changing energy around. But for an equation, that's the equation for the first law that you should know. And then this is the change in internal energy. This is the heat. This is work. And this has units of joules. This is all energy, so everybody's joules. Internal energy consists of all the potential and kinetic energy that is in a system on the microscopic level, this bottle, you can take that be at it's zero in gravitational in the gravitational field, and it's not moving. So this would have zero kinetic energy, zero potential energy. But if you look at the water molecules, they're screaming around at probably about 200 meters per second, and there's trillions of them. So if you added up all that energy that they have, it's a huge amount. It's just that they're all canceling each other out. So there's a huge amount of kinetic energy, but then there's also a huge amount of potential energy in these molecules. And the potential energy is just that. It has a potential to do something. So these molecules, wherever they are, they have a chance of reacting. So where is the potential energy stored? It's hidden away. Where is it in these molecules? If you were in my 1170 class, you should remember I asked this question like 6 months ago. Where would you hide that energy in a molecule?
Hydrogen bonds.
Well, that's part of it. That would be any kind of bond. That's true for intermolecular forces. And the bonds are the electrons. So all the energy that is capable of being used for chemical energy is stored in the bonds. And hydrogen bonds are intermolecular force that's based off of that same idea. So there's potential energy and kinetic energy, and a lot of it we can't really measure. It's hard, or it would take a long time to figure out how to calculate. So it's all hidden away there, but we can determine it by the heat and the work that's done. So this change in internal energy. You should know this. So a very basic question here: if heat leaves a system, so we consider a system, is anything that's under study. Everything else in the universe is the surroundings. Usually, you just consider the lab. So if heat leaves, what's the sign on the heat leaving? Positive or negative? Negative. That's exothermic. And if heat is going in, then it's positive. Now, if the system does work on the surroundings, so it works the same way. So if heat leaves, it's negative. So if the system does work, kind of pushes out on the surroundings, then it's negative. And if the surroundings do work on the system, then the work is positive. Now, that's always going to be the case here. Some books, though, they shift that. So their first law will have a negative sign here. All that means is that these have been switched, in case you see it. I saw it for the first time on my physical chemistry final. The professor came in and he was looking. It was an ACS, American Chemical Society exam, and he said, "Oh, let me just point out, this should be a negative. Everything we learned for an entire semester, this was positive, and it's okay. It's just how you define it." But he says, "Yeah, so just remember that. So anytime you have work, just change the sign." And we're about to go into the final. I was like, "Okay, I'm not even sure what you said there, buddy, but okay." And so it makes a huge difference, though. Like, I'll just show you with this calculation. But I just remember that. And he thought that was nothing. And he's right. I mean, all you do is anytime you saw work, you just change the sign. Well, this is what it's going to be. This is what it usually is. That exam was more or less a fluke, but enough to kind of freak me out a bit when I at least needed that. Okay. Now, so for the only calculation I can ask here from this equation is I just describe a system and a surroundings, the heat, work, and then you decide what the internal energy is. That's what I usually do. So a system absorbs 20 joules of heat and does 11 joules of work on the surroundings. And surroundings, you just put SURR. And the surroundings and the system together, those make up the universe. If you ever, sometimes they'll do that. So a system absorbs 20 joules of heat and it does 11 joules of work. What is delta U? Okay, so for this one, I guess I could give you delta U and ask you for for one of the others, but this is a good one just to check and make sure you know the signs. For Q, it's 20 joules of heat was absorbed. So is that positive or negative? Positive. So you write it as 20 joules. And the system does 11 joules of work on the surroundings. If it does work on the surroundings, picture the work is going out. It's not like heat, where it truly is a movement of the heat, but you can say the system does work on the surroundings, so it goes out, so this should be negative. So it'll be the numbers will be very simple. And what's nice about this, I can make up 4 different versions of the exam. I change this to emitted, or make this surroundings does work on the system, and I just flip-flop, and then there's 4 different answers, where each of this is either positive or negative, depending on the wording. Hardly takes any effort to do that, and that's what I usually do. So some people will have 31 as the answer, some people will have negative 31 as the answer, positive 9 and negative 9, just by changing a few words. So just make sure that you understand what these signs are saying about it, and you should be okay. All right, so not too much more we can do there with the calculation. So compared to what we've been doing, that's not exactly horrible. Adding a couple of numbers. Okay, now we're using internal energy here, but chemists don't like to use internal energy. We want to use enthalpy, the heat of reaction. So it's good enough for physics. It's good enough for the foundations of the universe, but chemists say, nope, nothing doing. We're doing it our way, but there must be a reason, because chemists don't want to work any harder than anybody else, so there must be something going on here. So instead of, we like to use this term for the heat of reaction, rather than finding the internal energy of a reaction. All right, so first thing is that, so the heat at constant temperature is equal to the enthalpy. So as long as we don't change I'm thinking the wrong thing here. Constant pressure. So this is heat at constant pressure. So this is true in thermodynamics. If you see any term and they have a subscript here, that's P or V or T, it means that thing is kept constant. So heat at constant pressure, and the reason chemists use that, because in the lab we rarely change the pressure. Everything's open. The beaker's open to the atmosphere, so the pressure is going to stay the same. So if we do that, if we're assuming we're at constant pressure, then we have this. Oops. Like that. So now we've incorporated enthalpy into this by making the pressure constant, then the heat is equal to the enthalpy. Then here's a little, I'm not going to go into the derivation here, but the work is equal to the constant pressure times the volume change. What I can say is this: if you have a cylinder and you have a piston, and inside here, you're let's say you're just producing, you have HCl and magnesium, and you're producing hydrogen gas. So as the hydrogen gas expands, if you want to keep the pressure constant, that means that the piston gets moved up. So that means this is the system, and the piston is moving against the atmosphere. It's moving against the surroundings. So after the reaction is over, the volume was smaller, now it's larger, which means the final volume is greater than the initial. This is positive, so the work is negative. If this compresses down, then the final volume is going to be less than the initial. This will be negative. With that negative, it becomes positive. So if the system expands against the surroundings, it's going to be negative. If it gets crushed by the surroundings, it's positive. So that's where we get that negative and positive for the work. But the main thing here is that you can then alter this first law again into that form. You won't have to do it. I'm just trying to show you why chemists do it this way. And then if you rearrange this, you get this. This thing, as I said, is from the heat, and we know that the heat can be found from this equation. So the upshot here is you can find delta H using a thermometer. The internal energy and the volume change and all this stuff is locked away inside there. If you want to find delta U, then you need to use a thermometer and then a cylinder piston for this part. So if you don't like chemistry lab now, imagine every single lab we did where you put everything into a big cylinder, put it all in there, get it all set, and then put a plunger in there, make sure that it works right, it's smoothly moving, but it's not letting any air out. And then you do the reaction, and the piston goes up a millimeter. Okay, millimeter, and multiply it out. Take the height times the surface area of the cylinder. Okay, and then you'd have to add that in. You'd be pretty miserable, so would I. So we just switched it around so that all we have to worry about is the heat of reaction, which is all we're interested in usually anyway. How much heat is being given off? So delta H, so that's why we do it. So on the exam, I could ask that, why do we use the enthalpy? That way, and you can just say, so that we don't have to consider what is called, this is known as PV work. And if we had to look at the internal energy and we were producing or using up gases, we would absolutely have to. Even in systems that didn't produce any gases, if it produced heat, then the liquid or aqueous solution is going to expand. We'd still have to take that into account. It would be a mess. It would not be fun. So you should know a couple of things here. You should know that this is true, that the heat of reaction, or enthalpy, let me just state that. You can call it the enthalpy or the heat of reaction. So the enthalpy is equal to the heat at constant pressure, but it has to be at constant pressure. As an aside, the heat at constant volume is delta U. But if you want to study that, you can't have the system change in volume. So you need to use what's called a bomb calorimeter. You put the reaction inside this thing. It's made of stainless steel. It's about the size of a peanut butter jar. And you put on the cap, and you have to rotate, spin it on about 30 times. And then you put it in, and through an electric conduit, you set off the reaction, usually an explosion inside. That's why it's called a bomb. But it's a badly made bomb because it doesn't explode. It doesn't even make any noise. But it does heat up from the explosion inside, and it gives off that to the water. Well, as long as the reaction didn't gain in any volume, then this is true. So in a physical chemistry lab where you use the bomb calorimeter, that's what you find. If you have to take physical chemistry down the line, I am trying to get a bomb calorimeter for our lab. Seems to be hitting. It always stops when I say it's a bomb calorimeter. Bomb. I say, yeah. It has the unfortunate name of bomb calorimeter. So bomb. I say, yeah, I know. I always want to say to them, well, come to the chem lab. I said, I can make several bombs up for you. We don't need to order one, so I can make them up on my own. But I really need is a few items that we already have. But yeah, that throws people off. So it might be a while till we get something like that. But when we get here, I always think when I was in physical chemistry lab, and we did this out, and this is because when you have a burning reaction inside that bomb calorimeter, this is going to be negative, and so is this, guaranteed. It's exothermic. And we did out the lab, and then I was looking in the lab, and it showed you how to do all the calculations. Well, in the physical chemistry lab, it's like 20 pages of calculations. And when I got done, I had the answer. It was so many kilojoules, and I was looking, it was positive. And that's what the lab said. It said it's positive. So at the end, I said, it's exothermic. It's got to be negative. So I'm just sitting there just before the lab. I was about to turn it in. I'm just looking. I said, nah. And I just put a little minus sign. And I turned it in. I said, it's negative. It's not. And then we get back to labs whenever the professor turned it back, 3 or 4 weeks later. And he comes in. He's very professorial. And there's maybe 12 of us. You realize that you did an exothermic reaction, don't you? And went, yeah. Well, only one of you made it negative. And I was like, oh my God. This is the first time I'd been constant. Yes. That was me. I was looking around. And he's like, says, I don't know how you could have missed this. He says, but only one of you got it right. And he's coming over to me. He's like, oh man, just lay it on me. Here we go. And he says, Mark, how'd you do that? And I was like, I don't know. It just threw me off. It was like, because he was thinking, well, if somebody smart had done it and Mark had done it, they must have worked together. But Mark, only Mark. This is just throwing him. He's just like looking around at everyone. I was like, look at all these smart people, Mark. Did you just accident? Is that just like, were you just dragging your pen across it? It's just horrible. So I was like, thank you. Anyway, so that's bad when you get the impression, because you think you're doing okay. And then the professor's pointing out, it's like, anyone but you, Mark. Anyone. Look at all these people. Anyway, that's what I always remember there. So I started just doing things to get them done rather than accolades, because they weren't heading my way. I could see that. All right, so the first law. Well, he's probably dead now. It's got to be, right? Well, it's actually, no, because I do know a couple of my professors are still going. See, what is that? That's 35 years ago? Holy cow. Okay. No, not 35. How old am I? No, like 30. Okay, so I'm not that old. All right, but I'm getting there. All right, so first of all, you should know this. You should be able to do a basic calculation there. You should know these signs. Make sure you know these signs, and then know the how to say these equations in words. Okay. Now, the first law, among other things that it guarantees, the first law says no perpetual motion machines. The key being machines. There's perpetual motion. Electrons are whizzing around atoms all day long, have for as long as that atom existed. No perpetual motion machines. Now, if you took a canister, let's say weighed 100 kilograms, and you flew it out you went out to intergalactic space. There's nothing out there. There's just a few hydrogen atoms here and there. And you got this thing spinning around out there in space. You got it just whizzing around, and then you left. Then you went home, and then, several generations, kids, grandkids, great-grandkids, great-great-grandkids, and then you went great-great-great-great-great-great-great-great-great-great, 1,000 greats. So 20, 30,000 years have gone by, and your descendant says, I'm going to go back and see. So about this cylinder that I've heard so much about. So they go fly out there, and they find the cylinder, and it's spinning at the exact same rate. Maybe slightly slower, but probably not perceptible to the because it'd be hit by stray radiation might do something. Okay, but then they decide to hook up that device to a generator to collect that energy. What happens to the cylinder then? It slows down, eventually stops, because the energy that was in there, it was spinning around because nothing was stopping it. But now you've transferred the energy. The energy gets transferred to the generator, and it stops. So perpetual motion machines are not possible. That is where you can do work. Perpetual motion sure. You can leave something that will spin probably for the next several trillion years. But if you want to do work with it, you're going to have to transfer that energy. That doesn't stop people from trying. Usually with magnets, they have these. If you go into any science museum, they usually have all these different perpetual motion machines that are based on magnets pushing off from each other, and because there's no real friction except in the axle of whatever's spinning, they can go a long time, but they always come to a stop. So the first law says, nope, can't do it. All right. So now, the first law also says, there's something I can, this page. All right. Yeah, that's good. Okay, this is 21, yeah. So if I take this and rip it up, and then I throw it on the floor, now it should reform and jump on the table. And I asked the first law, I said, is that okay? He says, sure, that's fine. the amount of energy it takes to get those things to form back together and jump on the table is minuscule. It's probably maybe 20, 30 joules. There's so much latent energy in that floor that if we took all the latent energy and the heat energy in the floor and pumped it directly into this desk, it would go through the roof. There's huge amounts of energy. So first law says, yeah, no problem. Then the second law says, not so fast. So the second law, that's the one that's a little bit more mysterious. The second law is, I'll read it off here before. So it's based, where is it? Okay. They don't have it here. Okay. The total entropy of a system and its surroundings always increases for a spontaneous process. What do we have here? What did I say? Did I say entropy? Yeah. So we got a few things to deal with here. The total entropy of a system and its surroundings. That's really important. Okay, so the total entropy of a system and its surroundings always increases for a spontaneous process, so that's an important one too. Okay, so entropy. Well, entropy is, another way of saying it is chaos, it's randomness, and so the randomness in the universe always increases with a spontaneous process. Now, the standard, this is a hill here, and you have a rock up here, boulder, and it goes rolling down. That's a spontaneous process. But if you have a boulder here and it goes back up, and you're just walking, you see this big boulder, it's got to weigh 10 tons, and it's just standing there, all of a sudden it goes, it's like, you're going to stop. Say, well, what the hell was that? Because you know inherently that can't happen. So if it went up, then if you're watching it on TV nowadays, you wouldn't be surprised that somebody has ran it backwards. That was a huge thing, though, back in the 1920s. Remember when they started running films backwards? It drew raves. They're going crazy. But the reason they knew it was crazy is if somebody dove into somebody was in a swimming pool and then jumped back up dry, you knew there's something wrong. Well, that's because of the second law. But that's inherent in us. We know that can't happen. We know that a boulder can't roll uphill. That's non-spontaneous. So this is non-spontaneous this way, and we just know that certain things are not allowed, and then this would be spontaneous. Somebody jumping out of a pool and not only landing perfectly on a diving board 20 meters up, but also perfectly dry, we'd have to suspect there's something wrong. And the second law says I deny you that. Somebody, maybe jumping up 20 meters is too much, but somebody could certainly jump out of a pool back onto the side of the edge of the pool, but being dry would be tough to do. Second law is the thing that says, you might have the energy to do it. There's energy enough to put those pieces of paper back together and make it jump on as a sheet back onto the table. But the second law says, no, we got a few problems here that we have to deal with because of this entropy. All right, so now here's the thing. Entropy, there's a book about Elric of Melniboné, and he wields the black soul-stealing sword called Stormbringer. And Elric, he has the misfortune of being able to remember all of his former lives. In every life, he is used by the Lords of Chaos to fight the Lords of Law. The problem is that he's had an infinite number of lives, so he goes stark raving mad each time he's reborn. And he's also pretty evil because he has a sword that destroys, not only kills someone, but steals their soul and uses it to energize him. So Elric is a servant of entropy, the Lords of Entropy. So whenever I see that, I always think it's a good book, Elric of Melniboné. Anyway, but the writer went with this idea of entropy versus law, chaos versus law. we're always trying to organize things, get everything in order, and the second law is constantly destroying that order with entropy. It wants more entropy. The universe is heading out to become more and more random every single time you breathe in, every time your heart beats, every time anything happens that's spontaneous. The clock is moving. That's causing more entropy in the universe. And there is a theory that if the universe doesn't collapse on itself, it will enter into what's called the heat death. Everything will become so totally random that everything is the same temperature. If everything's the same temperature, really low, no work can be done. You need a temperature differential to get work done. So maybe in 1 trillion years or so, our descendants will have to monitor their entropy. The kids will say, "Can I go out and play today?" So, no, sorry. You got to just sit quietly and just breathe really slowly, because we're rationing our entropy today. Because it could be that this is the only universe, there's nowhere else to go, and when that runs out, then everyone's the same temperature, everything is the same, and everyone just kind of keeps floating out. I think it's kind of relaxing sounding. So you're just walking along all of a sudden, and then you just float off into the universe forever. It's like, It's like just watching TV. Of course, TV's gone. But that's it. So everything's moving, and then everything stops, and that's the heat death. So every object in the universe just expands out forever at near zero Kelvin. Okay, so that's based on this second law. So the second law is also the thing that gets you when you're feeling like, it's like, life's out to get me. Say, sure, shit is. Second law is out to get you. Second law is after us all. Second law is the thing that every time my cells divide, they divide slightly wrong. And because of that wrongness, I get older. That's one of the main reasons that you age, is that your body no longer is replicating itself properly. So your hair, it changes your skin, and it's radiation too, but it's the second law that says every time some chemical reaction occurs, the really complex ones to split your cells, just slightly off. Every one time. So by the time you hit about 35, the second law is starting to take over. And you go down this slow, steady decrease towards American House. And that's it. So the second law is defeating us every single day. Now, here's the deal. Let's see if you know your statistics here. Now, if we have, you have 3 cards. The king, queen, and the jack. And what you want to do is you want to take those 3 cards, and you want to pick them in order. You want it to be in this order. You can't see the cards, of course. You have them face down. What's your chance of getting a jack? Just randomly. 1 in 3. Now, you got that, and say, okay, good. What's your chance of getting a queen then? 1 in 2. And then, so, what's the chance of getting them all in order the first time? What's that? 1 in... It's actually 1 in 3 factorial. And that is, a factorial is 3 times 2 times 1. And that's how it's set up. So how about for a deck of cards? That's 52 cards. What's the chance you spread them all out, they're all randomized, and you pick up whatever order, I don't know what the order is, say the first card in the box was 2 of hearts. What's your chance of getting a 2 of hearts? 1 in 52. Yeah. How about the 3 of hearts? 1 in 51. And go on. So, to put an entire get an entire deck of cards in order is 1 in 52 factorial, which is, I hope this has it on here. I think it's like 10 to this, 52. Oh, there it is. See what the second law has done to my eyes? They barely have, here we go. So 1 in 8.07 times 10 to the 67. The chance that you're going to get all the cards in order the first time is something beyond, if every person on the planet were to do this experiment and did it a trillion times a second, it would take probably, I don't know how long it would be. It'd probably be, it was going to be much older than the age of the universe. So you can't do it. It's not that it's impossible. It's just so unbelievably improbable to get this one thing to happen the way you want it. If you're off by 1 card, you have to start again. So this is the problem. This is what we're dealing with. So when you feel like things are not working out, it's because you want one thing. Let's say you want to meet your friend at the movies. Well, you have to make sure that you get there. There's no accidents. There's no construction. You have to make sure that your car works. You get to the movie theater. You got to make sure the movie's running. You got to find your friend. You didn't go to the wrong one. All these things have to happen to get you there, and that's just to go to the movies. How about getting a degree? Think about that. One thing you want to get. All these classes, everything that has to happen to get you to your degree. So you're up against it. The second law. Now, the second law also says that everything that can happen has an equal probability of happening. So you want to get, so this is 1 in 6. To get these 3 cards in order, you're only going to get it to happen 1 in 6 times. Even because the other 5 and 6 things can happen. So every time you try something, there's a chance of failure. If you're trying to do hundreds of things in a row, all of that adds up. But let's look at this cards. Let's say you do out those 3 cards and it doesn't work out. What do? Do it again. Maybe it doesn't work out again. Do it again. Do it again. Eventually you're going to get it, and that's how you defeat the second law. So if you ever feel like a light's out to get you, it is. The second law just is, you say, I want one thing out of literally trillions of things. And the universe says, well, I'm letting everything happen. So if it doesn't go your way, what do? You keep going. There's some times when well, this morning, I got this Jimmy Dean thing that you put in a microwave, and it has this little egg. You open this thing up, and it has egg in it. You pour it in and put in the mixings, and you put it in the microwave. It's actually not bad. Well, I got up, and I took the little inner egg thing. I shook it up. I got this, and I went to put it into the bigger cup. It caught on the edge, flipped the cup over, egg went everywhere. I was like, I'm going back to bed. Now that's your intention. You think I've been doing this for years. That is never. I always do that. That never happened ever. I was just like walking around. The cats are running away. Like, what was it that time? But it was possible to happen. And maybe it was that 1 in 100 times, and it happened. I say, oh. So I just had oatmeal or something. I don't know. Anyway, but the thing is that I didn't give up. I was going to just say, I'm going to bed, call the secretary, say I'm sick, but I didn't. And I've done that all my life. Every time I feel like I can't do it, I say, it's that damn second law. It's out to get me. You go there, you hit every traffic light. How unlikely is that? It can happen. And it happens at the worst time. Anyway, so second law, so I say that, so I don't know if that will help you, but sometimes you just feel like things are not going your way. It says you're trying to get one thing out of an infinite number of them. And the second law is the thing that's standing in the way. It's not a sentient being that's after you, but it's just saying, if you want something, you're going to have to try. Sometimes you're going to have to try real hard at it. So keep at that. Now, as far as the equations for it, it's this. Oh, what is this? Okay. Oh, this is what they say. Yeah, entropy created. Okay, so the entropy, so this is the change in entropy is equal to the Q, the heat, divided by the temperature, plus the entropy created on the microscopic scale. That's a word, right? Unknowable. Can't know it. I mean, you can calculate it, and it's actually the basis for what's called statistical mechanics. You take quantum mechanics and thermodynamics and combine them together, it's called statistical mechanics. If you are into theory, that's what you want to do. Statistical mechanics, very little has been done in it, not because people aren't trying, it's just unbelievably difficult. And the class that I took, it was just unreal. The exams went on forever. The professor, after 3 hours, he said, you do understand the law of diminishing returns? I said, I'm staying here until I have to use the bathroom. So I'm going, and he'd let us go. It didn't make any difference. It was horribly, horribly tough. But that's statistical mechanics. Now, I do this out because I'm a theoretician. I love this stuff. This is what you do in grad school. We make this stuff up, and you do it on a more, on a basis where you can maybe publish it. Most of the time, you're just goofing around. But statistical mechanics. One of the things that we did was we studied if you have a pop can, what's the chance that the pop can on its own, without you touching it, is going to pop back up and sit straight? And that turns out to be something on the order of 1 in 10 to the 23rd raised to the 10 to the 23rd. Because you're talking about moving a mole of atoms up into a different position. So the chance that you would get this, so if you just leave it there, and there's no wind or anything, nothing like that, you just have it there, the chance that it's going to jump up is almost inconsequential. But you can calculate it. You can calculate how much, what's the chances those papers will come together. One of the things that we did, I don't remember what the number was because there was so many atoms, but you could also calculate, like I'm walking to the wall, there's just atoms, there's just electrons here. What's the chance I'll pass through the wall? Now, if I pass through the wall, I'm going home to think about things. But that there is a chance. It's just very low. So the second law says, yeah, everything's possible, but it's just unlikely. Now, how you get around that, too, is the many worlds theorem. There's an idea that there is an infinite number of universes that are parallel to our own. And it was put forth because in quantum mechanics doesn't deny it. Quantum mechanics can't say that it's wrong. So it is possible. So in all of these infinite number of universes, anything can happen. In some of the universes, one of you is up here teaching, and I'm the student. And maybe everything else in the entire universe is the same except as this one, except the cap is on this bottle. And that's the only difference. That's the only conceivable difference. So with all of those different universes with an infinite number, there's one of me, infinite number of me heading to the infinite number of walls, and one of me went through. And so I like to think that that's the case. I always hope it's me. But it doesn't happen. Okay. So the second law, you should know this. Now, this is tough because we have all this unknown stuff. So we try to avoid the unknown stuff. And so we just write it like this. This is the equation you should know. We can't say what the entropy is, but we know that it's greater than Q over T. Good. There's some extra stuff here. We just don't know what it is. All right. So, let's see what we got here. Yeah. All right. Yeah. Do that, second law. All right, so the next calculation is pretty long, so we'll take a break. We'll get through the three laws, and then I'll do the calculations for last week's lab, or 2 weeks ago lab. What's that? What's that?
Didn't you say there was 4 laws?
3 laws that we have left. Yeah, 0th and the first. Yeah. So, yep, you're right. So 0th, 1st, and 2nd, and 3rd. So take a 10-minute break here. Don't forget. I'll get them and I'll have them by grade night.
Oh no, what did you do?
You didn't take it late. But people who took it late. Yeah, no, I have it. Yeah. After lab. I would have got around to it. Does that bother you? Well, thank you very much.
Okay, but still. What do you mean, yeah?
Okay, what happened?
Oh, okay. Wait, wait for your drink.
Find somewhere that you want to be thumbs
Like, girl. I'm Tori with. I'm Tori with. Like crazy.
I think I'm starting to take pictures of this crazy pack. I was late on the pool, so I wasn't really trying to see my window. Because I was the person, because I was hungry.
Let's go.
Yeah. I was trying to
Okay, you don't have to finish.
Oh, yeah.
Oh, you got it?
You said tea time?
Okay.
That's a lot.
That's a lot. But they don't.
Semi on the side of the road.
But the songs are not full songs. They're not full songs. Because they, because one is one dance, one song. 21 teachers, one song. And the song is a minute and 30 seconds. Oh, no, I gotta wait. But you got that. I feel like once you go back, first one, I'm going to be involved.
How long were you there? An hour. It would be interesting, I feel like. Well, like, no. I mean, yeah.
So those on Friday.
Their mom.
I'm ready to go back there now.
They all do.
You know what you did? You don't necessarily have to. These guys sound like you go behind.
The son is still mine.
But the thing that I was
What'd you do? Press your mattress or something?
how many songs was playing? Because the DJ stopped.
I told my parents that after she was talking, I took it, threw it out, gave me their mattress. And
How keep going?
it was halfway through last semester. But then I gave it to
I've had the same mattress for 13 years, maybe 14 years.
We were.
and my dad
But I see that you don't have to spend that money. You can rent it for $100.
And his parents were going to throw away the big mattress. So he now has a bigger mattress and it's really small. And dude, it fits, it's like the perfect fit. There's like this much tolerance between the mattress and the bed on both sides. So it's or no, because the queen.
it has like just a small sliver of space. But the design I don't know.
It's just amazing how finding furniture deals. Yeah, 3 couches. They're on top of like $3 and they're all in perfect condition. Got it from like a family member.
Usually so.
And I mean,
I mean, you gotta go.
See these people. Like I was there when I
Where'd they go?
I don't know where they went. They wanted to. It was a secret that my dad wanted to. I was like,
Was the Mediterranean?
it's so good. But I think that I just
I was in heels, I felt. I was in flesh, I felt. From like walking, you know, I'm 95. And like, I'm just like walking, like there's like a couple on my phone to their table.
Everyone knew Christ was from.
That really sucked.
was it expensive?
Not really
is like,
sucked.
what are you doing?
I would wake up,
Shadow for
and I
half.
would tell them I'm not running. Nothing. Water. I see water. That's it. I would go Disneyland, but it's your eyes playing illusion. You're not.
Like, it was so like, close. It was so funny.
This is the front of my mom. If you fall there,
Yeah.
we get lost.
The other kid just didn't help.
All right, so the entropy change for a phase transition is special, where the the change in entropy is equal to the heat divided by temperature, instead of being greater than. But the only reason this is because the phase transition, we assume that the phase transition actually, in the thermodynamics books, will say the phase change takes place over the course of infinity, or eternity. It takes an infinite amount of time. But this is a pretty good approximation, and so you should know this. Now, we also know that if this is at constant pressure, like we usually do, that the change in entropy will be equal to the heat of reaction over T. So we can do a calculation here, and here's how it'll be set up. We'll just use what we got here. So they have this reaction. Okay, so changing a liquid, carbon tetrachloride, to the vapor, and we're always going to assume we're at 25 degrees Celsius. That's standard temperature for thermodynamic data. That the heat of vaporization is 39.4 kilojoules. So the energy required to take this liquid and change it to a gas is this many kilojoules per mole. So we could ask, actually, we don't want to do that. We want to do how much, what. I'm in first law here. Second law is delta S. So what is delta S when 1 mole is vaporized? What is delta S when 3 moles of carbon tetrachloride liquid is vaporized? Let's see. And how about 4 grams that's vaporized? Okay, so we can do it for 1 mole, for 3 moles. So we always do it for 1 mole, because that's 1 mole here. And then if it's in moles, whatever our answer is for this one, just multiply by 3. Then this one we have to change to moles first. We'll do all 3 of them. All right, so we've got a few things that we have to consider here. Delta S is given in joules per Kelvin per mole. And it can also be just given as joules per K if we're not concerned about a reaction, where we're not concerned about moles. So it's joules per kmol or just joules per K. But that means that, what do these units have to be here? Yeah, that has to be joules, but we're given in kilojoules, so make sure you change to joules. This is easy. I mean, you could certainly make this 39,400 joules, but that's a large number to write. So what you would do is you'd say delta S is equal to 3.94 times 10 to the 4th joules per mole, divided by 298 Kelvin. So make sure you change to Kelvin too. Okay, so what we find is that everything has a randomness, even something that doesn't seem like it's moving very much. If you looked at the microscopic level, the molecules are oscillating around. There is some inherent entropy. So what we're going to do is, so the entropy of carbon tetrachloride gas is equal to the entropy for, the entropy for carbon tetrachloride gas is equal to the entropy of the liquid plus delta S. So everything has an inherent entropy, and that's what the third law is about. We'll see in a bit. So in the book, they say that the inherent entropy for carbon tetrachloride liquid is 216 joules per K. So the liquid has an entropy. It shouldn't be 0 because the liquid molecules are roaming around. And then we have this plus S. So first thing is we're going to find this, and then we're going to add it in here. So we have it here. So it's 3.94 times 10 to the fourth divided by 298. So this is 132 joules per K. And since they only use K, I won't worry about that there. It will assume it's for a mole. So what you want to do then is 216 joules per K plus 132 joules per K. So 216 plus 132. So the gas has an inherent entropy. Inside of it is 348 joules per K. Now that's if we're vaporizing. This is the heat of vaporization is what we're using here. Yeah.
Where'd you get the stand, Jacob?
Oh, that was given. So this is the entropy of the liquid before it vaporizes. So it already had a randomness. Okay, now we could have done it this way though. That's for carbon tetrachloride liquid is going to be equal to, let's say we liquefied it. We went the other way. We flip that reaction around. So this would be carbon tetrachloride gas. And then what do we do here then? Do we add the delta S? I guess in a way we do. But we're going from a gas to a liquid, so we're going to be subtracting it. So if we were to flip this around, this is the heat of vaporization, delta H vap. So if you flip this reaction around, then this is the heat of condensation. What do you think the value of the heat of condensation is? All we did was flip the reaction. Yeah, so it'd be negative. So on the exam, I could certainly give you the liquid, and I could tell you this value. So this would be 348. I could tell you that, and we're trying to find this. You'd figure this out, and this would be minus 132. So the answer would be 260. So just be aware of that. If I ask you to go from the liquid to a gas, we just use the positive value. From a gas to a liquid, it's going to be the negative value. So a few things there to remember, like the kilojoules to joules, that kind of thing. But all right. Yeah. Oh, I forgot to do. So this is for 1 mole. For 3 moles, you just multiply your answer by 3. The answer you get is going to be per mole. So 348 times 3. So this is going to be 1,044 joules per K for 3 moles. If you're dealing with grams, you have to change to moles first. So 4 grams of carbon tetrachloride. So this is about 154. And then for every mole, it's going to be 348 joules per Kelvin. So change to moles. And you're just multiplying by the number of moles. I gave you 3, so I multiply by 3. Here, change to moles, and then multiply by that number. So 4 times 348 divided by 154. So this is going to be 9.04 joules per Kelvin. So if you have less of the thing, you're going to have less of its randomness because there's less to work with. Okay, so that's one of the very basic calculations we have. Just make sure you know how to deal with that. And all I can do is change this sign here. It'll be a different number, but just change the sign if you go from gas to liquid. Okay, and this leads us to the third law. I'll erase this in a second. The third law gives us absolute entropy. We don't often get an absolute in sciences, so when you get one, you make a big deal out of it. And that's what the third law is. It just states that absolute entropy. So the third law. And so there's no equation here. A lot of good stories. Just has to be what it is. And I do like to go off with all the crazy stuff because that's what a theoretician does. And I always look out and gauge how many engineers and health field people I have in the class by that, because those people are more practical and very down to earth, and it's okay because you're going to make a lot of money. Theoreticians, if you're going to be a theoretician, you're going to have to teach. No doubt about it. I wanted to teach. But so if what I was talking about, this kind of flighty stuff, interests you, you're probably a theoretician. I didn't know that. I had to find that out the hard way. Started out as an experimentalist in grad school, and I said, what the hell is going on? And I said, let's do something fun. Let's see, and I started reading into the journal articles and finding some really fascinating stuff, at least to me. So, but if you don't, it's not an absolute test. But if you found what I was saying, it's like, what's he going to stop talking about this bullshit? It's like probably more practical, more down to earth, and that's fine. That's engineers and health field tend to be that way. There's only so many theoreticians the world can hold anyway. After that, it might get a little too bizarre. But just as an aside, so I would have liked somebody to tell me that all the time I'm cooking up all these weird ideas, and rather than doing the calculations like I was supposed to, when I was studying for, it's like, oh, that's why. I was a theoretician. Okay, so the third law, nothing much to say here, except that the entropy of a pure substance at 0 Kelvin is 0. If you have a pure substance at absolute 0, it has no entropy. It has no randomness. So if you look at a plot of this, is the temperature versus the entropy. That when we start out at 0 Kelvin, you start out at 0, and then it slowly makes its way up. When it hits a phase transition, there's a huge increase. So this is solid, liquid, gas. And the entropy just keeps rising as the things get hotter and hotter. But at 0, it's taken to be 0. So in a table, you'll see, we haven't talked about free energy yet. You'll see it listed like this. This will be the free energy of reaction, the heat of reaction, and then the absolute entropy. Notice there's no delta. A delta is for final minus initial. And we're always assuming the initial is 0 Kelvin. What's entropy at 0 Kelvin? 0. So we don't need that. That's why there's no delta here. You could have it, but there's no point to it. So in the table, you'll see, they give it here just S, and this is standard. Make sure everybody knows that. So anytime you see in the thermodynamics book, you see that little degree sign and it's not for a temperature, it must be standard. Even if you don't know what it is. It's some strange looking thing, some symbol, and you have that. That's it. If you see smiley face standard, whatever it is, they use a lot of different letters, a lot of different alphabets in books. But if you see that, you might not know what it is. Looks like a happy parameter there, but it is definitely standard state. So anytime you see that, that's what it means. Okay, so when you say absolute entropy, you should know that it's based off of the third law. At absolute 0, the entropy is 0. Okay. Now qualitatively, we'll just do the qualitative part here. And then I want to do talk about the calculations from last time for the labs. Okay, so if we have a calculation, or actually, I'll stop here because that's the third law. Oh, and the third law, well, no, I guess we can say that we'll save that for next time too. Okay, so that's the third law. So we got the 0th, 1st, 2nd, and 3rd laws. That's what they are. And but after that, we just are going to do a whole series of calculations for next time, so that's a good place to start. Okay, so we'll talk about the last week's lab, 2 weeks ago, and then we'll talk about today's lab, what you need to do. Okay, so you should have from your graphs, or you should make up your graphs when you get. There's 2 graphs we have. It's going to be for the acetic acid, NaOH, and then it's going to be the so the one graph should look like this in general. So once you graph it out, you can do it just using a ruler. You don't have to. If you can get the, if you have a program that will go through that curve, that's fine, and find this point. And then this one is going to be backwards. Okay, so what we know from the Henderson-Hasselbalch equation when these two are equal, then this term is 0, and the pH is equal to the pKa. So what point does that happen on the titration curve? It happens halfway to the equivalence point. When you're halfway there, half of this acid has been turned into into acetate. So when we're halfway there, we have this. So this is gone, and pH is equal to pKa. So let's say, just make it easy, that you have 20 mils here. Whatever your equivalence point, the volume is at equivalence point, take half of that. So half of this takes us to 10. Go up to the curve, and then over. Wherever it hits this is your pH over here. Since we're halfway to the equivalence point, these are guaranteed to be the same. So this is guaranteed to be 0. So pH is equal to pKa, and now we can find pKa. So for mine, I just took some numbers I think are close. If yours are different, that's fine. I'm kind of guesstimating here because I couldn't find the data that I wanted to bring. So we have this. So my titration took 20 mils. I backtracked to 10 up to here and over, and the pH was this. So we know that the pH is equal to the pKa, and for mine it's 4.75. So Ka is going to be equal to 10 to the minus 4.75, and I can find, and so that's all you really have to do. And this is 1.78 for mine times 10 to the minus 5. I think it should probably be 10 to the minus 5. Okay, this graph is a little trickier, but it's the same concept here. If you, let's say again, this is 20 mils. You backtrack to 10. You go up to the curve and over. And what I pick? Because I know this one's pretty close too. I have it at 9.2. This is your pH. But remember, your acid, so what you have at this point, you have ammonia and you have NH4. Of these, which one is the acid? Oops. Is this the acid? No. This guy. So what we're going to find, this is going to give us the pKa for this conjugate acid. So once we have that, we can then find the pKb for this and find the Kb. That's what we want. We're looking for the Kb for NH3. But this number but the graph is only giving us the pKa for ammonium. But we want the Kb for ammonia, so we have to do a little bit more work. So what this is, so the pKa for mine is 9.2. So if you take 10 to the minus 9.2, this is going to be 6.31 times 10 to the minus 10. And this is equal to Ka. But that's for the ammonium. We want Kb. So that's going to be Kb is equal to Kw over Ka. So everything works the same as here. But when we get here, we don't want Ka. We want Kb, so you have to do one final step. So 1 times 10 to the minus 14 divided by 6.31. And your numbers probably will be around the same. Whatever they are is what they are. That's fine. But probably looking. The Kb and for ammonia and the Ka for acetic acid are on the same. They're usually about 10 to the minus 5. So that's what you have to do with your graph. So once the other one's a strong acid, and weak, strong acid, strong base, and the weak acid, weak base. We can't do this. So that's for the results here. You're only to find the Ka and Kb for the weak strong combination. The other ones are just asked where's the equivalence point. Okay, so that's it. Yeah.
Yeah. So I didn't understand how we're supposed to find like the midpoint on the graph. Was I just supposed to draw a line?
Yeah. So you once you have your graph, you graphed it out. You should have it. It should have your volumes here. So for me, let's say it turned out this was 20 and this is 21. You just estimate. So let's say you come up with 20.5, then divide that by 2, and then just go back. You can be off even by quite a bit, but just eyeballing it just with a ruler, you should be able to get close. And that's all I want to see. You can just, if you have a program that'll do it, the way that you do the scatter plot on Excel, it doesn't seem to allow you to do the fractions here. It just takes one or the other. And I'm sure there's a way to do it, but I never figured it out, and that's fine. Just what I want to see is those graphs, and then do the calculation the best that you can. Okay. For today's lab, one last lab with the acids and bases. So, first thing is, let's see if I asked you to do. Oh, no, I didn't. I did change it. Okay. There's not enough room for everybody to have 2 burettes with an acid and a base in it. I guess technically there would be, but seeing 8 burettes on the same island looks a little cluttered. So what you're going to do, you're doing. So if you're at an island together, 2 of you will have an HCl and 2 will have NaOH, and you just switch them. You don't have to switch them, you just can move and do the. So one student will be doing the HCl titration at their station, the other does NaOH at their station, then switch. That will just free up some more room for you. But do your own titrations. All right, now here's how you set it up. You're going to have 4 beakers. Okay, so the first one is you're going to have 50 mils of ammonia. And this is your ammonia buffer. So it's going to start out at 50 mils ammonia. It won't be that high, but just sort of right in there. And then this is going to be 50 mils of water. I should say pure water. I just want to couple them together because these are 2 separate things you're dealing with here. So you're going to do the same titrations to both of these. And then you're going to have another beaker that is your acetic acid and acetate buffer. So this one's going to start out with 50 mils of the acetic acid. And then you're going to have its corresponding water. Okay, so the reason we're doing this, you're going to first create a buffer for this guy. You're going to get it at a set pH. Then you're going to add in, for this one, you're going to add HCl until you drop it to a low pH. Then you're going to go back to this buffer and try and put in enough HCl to get it to the same pH. This one, you got to be careful. Okay, first let me, what I have it here for you. Okay. So, first to create the buffer, add HCl until you hit 8.9 to 9.1. And if you go a little bit above or below that, that's fine. Okay. So you're going to take this, have it there, you're going to add in your HCl. The pH meter will show you, let's say you're at 8.9, just stop. Okay, so that one's set. Now you're going to take this, so add HCl until the pH, what do we want? 2.3 to 2.5. This does not take much. Sometimes students will have less than a mil to get there. So when you're adding in the HCl, the pure water, that's the whole point of this. What I'm trying to show you is that this buffer, you're going to have to add in a lot of HCl to get it to go to this pH now. But this pure water is just going to drop through the floor almost immediately. So create your buffer, mix in the HCl till you're at this pH, set it aside. Take this guy and add your HCl until it gets to pH 2.3 to 2.5. And if you overshoot it, you might put in 2 mils and it might drop down to 1. Well, it's just water. Dump it out and do it again. But just be careful. And some people, like I said, it takes less than a mil to get here. So once you do that, then do the same thing to the buffer. And I'll go through this again. Then you're gonna once you have this at 2.35, you're just determining how much HCl did you have to add to get here. That one's done. Then go back to the buffer that you've made and add in HCl until you get to the same pH. Try to get to the exact same. And you're going to find to the HCl you're going to add to the buffer, this might take 2 mils. This one might take 30. And that's just to show you how effective a buffer is. That makes sense? Is that good? Okay. We'll go back through it one more time after this. But okay, so we create the buffer. So you have your acetic acid, which has a low pH. So add NaOH until the pH is equal to where is it? 4.9 to 5.1. So the pH is probably going to be down. I don't know what the concentration is, but the pH is probably going to be around 2. So you're going to add in just a little bit of NaOH until you get it to this pH. Now it's set it aside. And then for this one, add sodium hydroxide until the pH into the pure water is 11.2 to 11.4. This one is the trickiest one to do to get it to this point. It kind of fights you a little bit, and then it goes nuts from what I remember. But just be careful. Again, this one won't take very much. So whatever this is, if this comes up to 11.3, try to make this 11.3. This one will be easier to hit. So if you make this, and this goes up to 11.6, fine. Just work with that. If it goes up to 12 or something, start again, because you're not going to get this guy to go up that far, probably. So just once you get it to some set amount, now you go back with this buffer and you try to nail whatever this pH is exactly over here. This one may take a couple of mils. This one's going to take a lot. I've seen ones that are over 40 mils to do it. So, but again, so what I want you to see is that you create your buffer and see how powerful it is. It actually can defend against strong acids and strong bases for an extended period of time. It takes this one a lot longer. Now, we changed the concentrations recently, so when I say 30 or 40 mils, it might be less than that now, but it's going to definitely take more than this. So the pure water should take not very much, and then the buffer should take more. All right, is that... Triple that. Any questions? Concerns? All right, so just one more time. So you'll have your ammonia in one beaker. Add the HCl until you get to this pH. You have your 50 mils of water here. That's your one set. This guy, add in the NaOH until the acetic acid has become a buffer of 4.9. You have our water here. And then to each of these, add HCl to get to the same pH. Do this one first to get your target, and then do this one. Find this one, get it up to 11 pH, and then whatever your target is, and then use this and add the NaOH. So 2 sets. So really, you have to do 1 titration, 2, 3, 4, 5, 6. So 6 to do. So take your time with it, get it right. The numbers will actually turn out really well if you take your time with it. So one person in the island will have the HCl, so you do this one, and then give the HCl to the next person. If you want both burettes, you can certainly do it. It just gets a little crowded from what I've seen, but that's up to you. If there's 3 people on an island, you'll figure it out. But make sure you do your own titrations. Is that good? All that stuff? All right, so head on over there. Might as well do this. And I do have the exams. Just remind me when we get over there.
Good luck with today's lesson.